This presentation is about analytical solutions for gravity changes caused by magmatic sources, triaxial magma sources. This work, I've done this work together with Eleonora Ribalta. So, as you could see in the previous presentation, we can use gravimeters to constrain the location and the mass change of sources of mass change, like new magmatic inflation, magmatic intrusions. Considering volcanic studies, we usually use deformation data to constrain the location of deformation sources, and by deformation sources I mean pressurized cavities. These cavities can be pressurized due to the intrusion of magmatic fluids or degassing within the cavity. So I simply in the following refer to them as deformation sources. The depth and volume change associated with these deformation sources can be well constrained by using deformation data involving, for instance, horizontal displacements or vertical displacements associated with the deformation period. And by using gravity data, the mass change associated with these sources can be constrained. But from the previous presentation, you might remember that we can also use the gravity data to infer the location of these sources. So this is a point to keep in mind for later. If we combine deformation and gravity data together, then we might be able to infer the intrusion density, which is very important for us, because this way we can say something about the underlying source of the deformation, and we can say something about the physics of the intruded fluid. We can distinguish between magma and water or other kinds of basically fluids that we have during the inflation period. So to put things in context, we consider a few examples. We know that a resolution of 1 microgal for gravity data is achievable by using the sensors that we have now. So a gravity change of 7 microgal can be caused by 1,000 kilogram of added mass 1 meter exactly below a gravimeter. And we can also consider that the same amount of gravity change can be caused by 1 billion kilogram of new mass at a depth of 1 kilometer below the gravimeter. But at the same time, 2 centimeters of vertical displacement of the gravimeter produces almost the same amount of gravity change. So this means that gravity data contain information on mass changes and vertical displacements. So but this is the key sentence in this presentation, and what I want to say with this is that we should not only focus on constraining mass changes by using the gravity data, and actually gravity data can offer more information. One of the issues that is usually overlooked is the deformation-induced gravity change topic. And what I mean by the deformation-induced gravity changes is represented in this figure. Here we have a magma chamber, a pressurized magma chamber, which has led to some surface uplift. So due to this pressurization and the deformation of the host rock, we have several contributions to the gravity changes that are measured at the surface, at this gravimeter represented by the inverted triangle again. So the different contributions have been listed here. Of course, the main contribution is from the fluids that are injected into the magma chamber, represented by this delta G delta M, the red term here. But all the other terms are caused by the deformation of the crust below the gravimeter. So the first term is representing the free air contribution, which is due to the vertical displacement of the gravimeter. The delta GSM represents the displaced surface mass right below the gravimeter, and delta G epsilon KK represents the density change throughout the host rock. This is due to the forces that are applied to the host rock by the pressurized magma chamber. And finally, delta G delta VC represents the contribution due to the volume change of the magma chamber. So there was no analytical solution for triaxial sources of pressurization, and this is one of the problems that we addressed within Newton G. In order to address this problem, we used the point compound dislocation model, which is a point source solution for modeling deformation associated with triaxial sources of inflation. The solution is composed of three tensile dislocations, which represent openings along different directions, and these openings can be different, and therefore their combination can represent any triaxial source geometry. We use this solution together with Okubo 1991 solution, which was developed to calculate the gravity changes associated with these locations. And this way we could develop an analytical solution for gravity changes associated with triaxial point sources. So a point source can be a good model for sources in the far field. Then by that we mean sources that are deep enough in basically their depth is several times larger than the characteristic dimension of the source. But if the source is in the near field, in other words, if we have an extended source at shallow depths, a point source approximation is not enough. So in these cases, we need to have a finite source model. And from the work done by Eshelby 1957 and Davis 1986, we know that the distribution of point sources like this in the figure in the middle can give us a solution for finite sources, a uniformly pressurized finite source. And again, in this case, you see a comparison between a point source and a finite source solution, and you see that for shallow sources, the difference can be quite significant. So we decided to use a distribution like the distribution represented in the middle to develop a solution for finite sources. The work has been already published in GJI, and basically we found a minimum number of point sources that are distributed within the cavity, but not as a uniform distribution. As you see, this distribution is depth dependent. We found a minimum number of point sources that can be put together in this configuration and give us the solution for a finite source. So you see that if we have the same cavity at different depths, we need a different number of point sources to simulate the surface deformations and gravity changes associated with this deformation source. So here we have done a comparison with existing analytical solutions. We see that there is a perfect match between our solution and another solution for spheroidal source. This analytical solution is only for spheroidal sources, but our solution is, of course, can be applied to any kind of triaxial deformation source. So our solution is quasi-analytical in this case for the finite, in the case of the finite ellipsoidal cavity model. But as shown here, it is extremely fast and still useful, very useful for rapid inversions. So here we compare the point source and finite sources that I introduced to you in the previous slides with a solution based on the finite element method. The solution is from Trazati and Bonafede 2008, and here are the source parameters. The cavity is located at a depth of 5 kilometers, and the semi-major axis is around 1,800 meters. Here we see three out of the 5 contributions I showed you earlier, and these are all deformation-induced components. And you see that there is a very good agreement between these solutions and the solution from, the analytical solution, the quasi-analytical solution, and the finite element solution. All of them match well, and the delta G here in this case represents the sum of all these 3 terms. This figure already shows that deformation-induced gravity changes can be quite significant, and they are not. We should keep it in mind that these contributions may not be negligible, depending on the source geometry. Now I basically say some points regarding coupled inversions of surface displacements and gravity changes. So here we have sources of different geometries located at different depths. If we adjust the sources well, we can see that in some cases we can have very similar vertical displacements. As noticed by Dietrich and Decker 1975, in these cases, from the vertical displacements, we cannot infer the source geometry and source depth uniquely. So if we look at the radial displacements caused by these sources, we see that they are completely different. The conclusion was that in order to constrain the source geometry and source depth, we need to have the vertical displacements and vertical and horizontal displacements, both of them. If we look at the deformation-induced gravity changes caused by these sources, we see that they are completely unique. And this tells us that we can use gravity data to infer the source depth and the source geometry, because the gravity data also provide information on these deformation source parameters. Similarly, we can play with the depth of these sources such that they produce similar radial displacements, but as we could guess, we see that the vertical displacements are completely different. Again, we see that the gravity changes associated with these sources are completely unique. This is all these results show that gravity data can provide information on the source parameters, not only on the mass change. Now we consider the different approaches available for joint inversions. Usually one practice that many researchers do is to correct the gravity data for the free air effect before the inversion, and then they carry out the inversion. We suggest that a better approach is to deal with the free air correction within the model, and applying the correction before the inversion is not a good practice. In order to show what we exactly mean by this point, we did a synthetic test, and here in this case we have a source of pressurization. You see the cross section and the top view here. The triangles represent GPS and gravimeters. So we have all the horizontal and vertical displacements and the gravity changes at all of these stations. So we use all of the observations to constrain the source parameters First, we use the method number 1. We apply the free air correction and then use the residual gravities to infer the mass changes. I have to say that in this case, we first use the deformation data. We invert them in order to constrain all the source parameters, and then we use the residual gravity to constrain the mass change. So this is what I mean by the separate inversions. Then another approach here is to correct the gravity data for the free air, but still do the inversions in a joint way, in a simultaneous way. And again, we see that the results do not change much in this case. And lastly, we run the inversions without correcting the gravity data for the free air effect before the inversion, and we let the inversion to do the correction. And this way you see that first of all, we have a smaller uncertainty associated with the volume change of the source, and much smaller uncertainty associated with the mass change. In this case, I'm not showing the other source parameters, but the improvements can be seen also on other source parameters, especially, for instance, on the source depth. So we applied our joint inversion technique to an inflation period at the Long Valley caldera. This caldera is located in California, and the geodetic network at Long Valley caldera is shown in this figure here from Pulbrienti et al. 2021. The data that we have for this inflation over 1982 to 1999 consists of leveling data, gravity change data, and baseline measurements. So the baselines are represented by these lines here, and all these red circles represent leveling and gravity data. So we perform a Bayesian joint inversion of all these data sets. In the first inversion, we use all of the data sets, the gravity, leveling, and EDM, and we can constrain all the source parameters. Here you see a few of them. We see the source depth almost at 7 kilometers below the surface. You see, and you also see the mass change associated with the source. Here, this is basically the inverted source located at the center of the caldera below a resurgent dome. In a second inversion, we use only the gravity and EDM data. So in this case, we are not using any vertical displacement. We do this in order to show that we do not need the vertical displacements for the free air correction necessarily. Although we don't use the vertical displacements, as you can see, we can still constrain all the source parameters. And in the end, again, we have the network at Long Valley. We see the fit to the gravity changes. So we have the data and model represented here in this figure. And although we did not use the vertical displacements in the inversion, we can still predict the vertical displacements from the model. And here you see that the predicted vertical displacements show an excellent match to the observed vertical displacements. This is confirming our claim method 2. And here are the conclusions. I just leave them like this.